Scientists have solved a 100-year-old mystery, discovering that glass found in the Egyptian desert was created by a meteorite impact rather than atmospheric airburst. The findings, reported in the journal Geology, have implications for understanding the threat posed by asteroids. The authors examined tiny grains of the mineral zircon found in samples of Libyan desert glass found over several thousand square kilometres of Egypt's western desert. Created some 29 million years ago, the canary yellow-coloured glass is nearly pure silica. One chunk was famously carved into a scarab that was part of King Tutankhamun's pectoral. The origins of the glass has long been a topic of ongoing debate as to whether it was formed during meteorite impact or during an airburst, which happens when asteroids explode as they hit thicker layers of atmosphere. The study's lead author, Dr. Aaron Kavosi from Curtin University, says the idea that the glass may have formed during a large atmospheric airburst gained popularity following the dramatic airburst over Chelyabinsk in Russia in 2013. The fireball and explosion, which was captured by dashcams across the city, caused extensive property damage due to the shock wave from the blast. Humans were injured mostly by shards of glass caused when the windows through which they were looking exploded. However, the blast failed to cause surface materials to melt. And that's where the Egyptian desert glass is different. Zircons in the glass preserved evidence of the former presence of a high-pressure mineral named Meteorite, which only forms during meteorite impact. Previous models had suggested that the Libyan desert glass represented a large 100 megaton airburst, but these new results show this could simply not have been the case. Kavosi says meteorite impacts are catastrophic events, but they're not common. He says airbursts happen more frequently, but we now know not to expect a Libyan desert glass forming event in the near future, which is a cause for some comfort.
The first studies of this glass were the discovery that, for one, it was very high in silica. And the issue there is it takes a lot of heat to melt something that's almost pure silica. Silica is just common beach sand, quartz grains.
Lots of it around Egypt and Libya, I guess.
Yeah, that's right. Well, at least today there is. Of course, this was 30 million years ago.
True,
Egypt was rather lush back then. So the climate today in Egypt did not look like it did when this event happened. But sand is pretty common. We still don't know exactly what was hit to melt, whether it was a quartz-rich rock like a sandstone or whether it was something more like desert sand. It's hard to tell that. But there's abundant evidence for really high-temperature processes. There's minerals that only form under very high temperatures. Some minerals melted or reacted away, another process that only happens at high temperature. And I think the science community for many, many years was happy with the idea that this was some type of an extraterrestrial process because those kinds of temperatures aren't generated by normal igneous rocks. You'll never find something from a volcano on Hawaii that's anywhere near this hot.
The debate was whether or not it was from an airburst or a ground impact.
That's right. So early on, I think people favored the idea that this was a meteorite impact because at the time there was a lot less research into how airbursts work and what kinds of effects they produce. And so I would say through the 60s and 70s, even 80s, the idea that it was an impact gained a foothold. But there was always some nagging issues. And those were, for one, there was no source impact crater that had been identified where the glass could have been thrown out of. So that was the first problem. The second problem is that an impact event produces unique conditions in rocks in the Earth. When you slam a rock from space into the Earth at about 15 kilometers a second, you generate shock waves. And the shock waves really squeeze the rocks like an accordion, and that process creates a unique kind of damage in rocks and the minerals called shock deformation. Deformation or damage that results from shock. And that type of evidence had not yet been found in pieces of the glass, and so that left room for other alternative hypotheses to rise up.
And I guess then we had the 2013 Chelyabinsk event, and that sort of brought the idea of an airburst into the picture much more strongly. And of course, people always in the back of their mind would have had what happened at Tunguska 100 years earlier in their mind as well, which was also an airburst.
Well, here's where things got interesting. people have wondered about the Tunguska event over Russia that happened, I think, in 1908, and that has generally been attributed to an airburst because, again, no source crater has been found. Combine that with advances in numerical modeling that came out primarily of nuclear weapons research design. And so people can do very sophisticated models of what happens when you detonate a nuclear weapon in the atmosphere. And because effectively what that does is it's a giant deposition of a tremendous amount of energy into the atmosphere, and there's all kinds of complicated physics that occur in that process. But great advances have been made in being able to model that, and that gave rise to people starting to say, you know what, the same or similar type computer codes could model this airburst process. And I would say that probably has been going on for 10 or 15 years in a modern way. And so the idea that, well, geez, a big enough airburst could really roast the surface of Earth with a lot of thermal energy. And guess what? It wouldn't make an impact. And because of that, there wouldn't be evidence of shock deformation. And so that seemed to fit the bill to explain Libyan desert glass as a sensible alternative hypothesis. And then, of course, the Chelyabinsk airburst happened in 2013.
But then you guys drilled into this, almost literally, I guess, a bit deeper, and you've gone back to the ground impact theory.
Well, here's the deal. The Tunguska airburst over Russia is modeled to have been about a 5 megaton event. Megatons is the amount of energy deposited in the atmosphere. The Chelyabinsk airburst is thought to be about half of a megaton, so even smaller than the one that happened in 1908. And the thing about Libyan desert glass is the way it had been modeled, it came across as a 100 megaton event. So a giant event compared to these historical airbursts. And that's kind of frightening if that's the case, where basically an asteroid thought to be about 100 meters in diameter could rip into the atmosphere and literally breathe fire onto the surface of the Earth and incinerate a large portion of it at very high temperatures. That's kind of a terrible thing to think about. This is what inspired another investigation of the Libyan desert glass that we started a year or two ago.
And so how did you do your research, and what did you find?
Well, one of my collaborators, Christian Kerbel, who's the director of the Natural History Museum in Vienna, had made several trips to the Egyptian desert to collect specimens of Libyan desert glass. Dr. Kerbel's specialty is impact glasses and detecting evidence of small amounts of the impactor that gets dissolved in impact glass when a rock from space hits and gets vaporized. And so there's some elemental analyses that are targeted to try to detect that. And he had previously detected such the presence of an extraterrestrial geochemical fingerprint in the glass. That still doesn't solve the issue of whether or not it's an impact or an airburst. We collaborated in our project. He sent me some samples of the Libyan desert glass that he had collected previously about a decade ago, and I took a look at them with a scanning electron microscope. My interest was to look for the mineral zircon, because zircon is a relatively common mineral in a lot of different rock types and also in loose sediment, loose sand, and it is an excellent recorder of shock deformation. And so the thinking was, we can take a look at some of these zircons, and if there was shock deformation from an impact, zircon would be a good recorder of that process. And so that was what we set out to look for.